Good evening. As usual, it's a great pleasure to welcome you now to the 10th Pancharatnam lecture. This lecture series was launched during the Platinum Jubilee year of the Raman Research Institute. And these are colloquium level lectures named after one of our very well-known scientists from Raman Research Institute, Professor Pancharatnam. He is an illustrious alumni of this institute. And we view this as a very prestigious series of lectures which are given by the top scientists and to reach out to people. So let me take this opportunity to tell you a bit about Professor Pancharatnam. So Professor Pancharatnam joined Raman Research Institute as a senior scholar, like many of our students here, in 1952. He completed his PhD under the guidance of Professor C.V. Raman. And Professor Pancharatnam was interested in crystal optics and discovered a subtle effect in the interference of polarized light, which is often referred to as Pancharatnam Berry phase. And it's very relevant to quantum mechanics, in terms of the geometrical phase, and used a lot in quantum and classical and quantum optics. So the Pancharatnam Berry phase has an interesting story. So Michael Berry discovered the effect 30 years later, and showing true scientific largesse when he was pointed out to this paper in 1956. He immediately published an article titled "On the Pancharatnam Phase" and more, and then to draw attention to the pioneering work done. And so this has continued to be an active area of Raman Research Institute, of course, now with the whole quantum buzz in the country and around the world. The fact that our institute had an illustrious alumni thinking on those lines way back in 1950s is very impressive. Professor Pancharatnam also devised the earliest achromatic wave plate for his optics experiments. And this is something which is a bit personal to me because this was recognized and used for IR and all that. Very recently, I myself came to know that the cosmic microwave backgrounds, which are the most frontline experiments, are using this concept for microwaves, millimeter wave astronomy. Unfortunately, Professor Pancharatnam passed away at a very early age of 35 in Oxford on 28th May 1969. So I would now request my colleague Shobhan to introduce the Panchar speaker. We are delighted to have yet another illustrious speaker, Professor Jainendra Jain. So over to you, Shobhan.
Yes, hello. So it's really a great honor to be introducing our eminent speaker, Professor Jainendra Jain. On a personal note, he continues to inspire me and other theorists working on many body systems, both with his professional achievements as well as personal journey from a very humble background. So his name should be familiar to all of you. Still, let me read out a formal introduction on his illustrious career. So Jain is a theoretical physicist in the field of quantum condensed matter physics with interests in the area of strongly interacting electronic systems. He is best known for predicting a new class of particles that he named composite fermions, and for explaining the phenomenon of the fractional quantum Hall effect as the integral quantum Hall effect of composite fermions. Jain is a recipient of the Distinguished Alumnus Award of the Indian Institute of Technology, Kanpur, the Oliver E. Buckley Prize of the American Physical Society, and the Wolf Prize in Physics. He is a member of the US National Academy of Sciences, the American Academy of Arts and Sciences, and a foreign fellow of the Indian National Science Academy. He has held visiting professorships in IISc, Bangalore, TIFR Mumbai, and ISA Pune. He is currently holding the titles of Evan Pugh University Professor, Erwin Mueller Professor of Physics, and holder of the Eberle Family Chair of Physics at the Pennsylvania State University. So I would now invite Professor Jain to tell us about the story of fractional quantum Hall physics and his pioneering contributions in it.
Well, thank you very much. And So when you just saw this string of letters, numbers, and symbols coming randomly, you probably think it has no meaning. It's devoid of any meaning. But it's not. It's actually something. It's an encrypted message. And if you know the password or the encryption key, you can just read the message. So, theoretical physicists, they have many different approaches, perhaps as many as there are theoretical physicists. But in my way of thinking about things, theoretical physics is not that different from this, So nature gives us lots of facts, and at first they seem baffling. At first they seem disconnected. We don't know what they mean. But we are trying, as theoretical physicists, we are trying to find the encryption key. So we are trying to find the fundamental principle that underlies those phenomena. And once you know that, everything suddenly makes sense. You can see, you can kind of read the message, and everything snaps into place. So this happens all the time in physics, this unification that leads to coherent understanding of otherwise chaotic facts is something that's there everywhere. But in this talk, I'm going to focus on a system of two-dimensional electrons in a magnetic field. And what I'm going to tell you that a study of this system has taken us into a very strange new universe, which is ruled by some very bizarre quantum particles. These are called composite fermions. They are electrons which have kind of eaten up some of the magnetic field. And they, in fact, give rise to some more exotic particles which are known as anyons or Majorana fermions. And these particles are so exotic, so strange, that they are not allowed to exist in a three-dimensional world by laws of quantum mechanics. And even in this system, nobody would have believed that they existed unless if the experiments did not prove their existence. Wolf Prize was mentioned in the introduction. So recently when I was awarded the Wolf Prize, my family kind of gotten carried away. So they said, okay, let's have a celebration party. And in that party, we had all of our friends, social friends who were not physicists. So my daughter, Saloni, who is very methodical, she put into ChatGPT the question, look, I'm organizing a celebration for this, 3 hours, how should I plan for those 3 hours? ChatGPT said, you should ask your dad to give a 5 or 10 minute presentation explaining to people what composite fermions are, what this fuss is about. So I first thought, how am I going to explain composite fermions to people who don't even know quantum mechanics? But then I remembered that a colleague of mine told me about this book. It's called Quantum Physics for Babies. In fact, I have 2 beautiful granddaughters, so I bought this book, and in fact, this is a series of many other books. There is like relativity for babies, and all parents in US have these books, okay? So I bought these, and I gave it as a gift to my daughter. She said, oh, I've already read these books to the granddaughters, okay? So anyway, I thought if we can teach quantum physics to babies, why can I not tell about composite fermions to the grown-up friends of mine? So I tried to make my 10-minute spiel there as simple as possible, and that was a spectacular flop, okay? So nobody got anything. My daughter said, Dad, you have to bring it down a few notches. So what I have tried to do here is to make it as simple as possible. I have removed all the technical details. And basically what I'm going to do is tell you a story with many amazing twists and turns as it goes. Whenever we feel that we have really understood things, something else happens and it opens a new door, and then you explore that, and when you feel, oh, we have understood, then something else happens. So we'll see how things work. This is like, this is not special to fractional Hall effect. This is not special to this field. This happens in physics all the time. So I'll begin by telling you about the unfolding of the fractional quantum Hall effect mystery. I will then go on to tell you that if you looked at the problem just theoretically, it's an impossible problem to solve. Okay. I will then tell you that the key, the encryption key, the fundamental principle that underlies this is called composite fermion. It's depicted like this, and we'll see hopefully by the end of this talk what the symbol means. We'll see that with this we understand fractional Hall effect. All of the disjointed pieces, they come together to make it's like, you're making a puzzle. Once you put together all the pieces, you see the beautiful picture. So hopefully we'll see that. And I'll tell you about some recent twists and possible future twists. So a lot of this talk will be just going through the memory lane and telling you about what happened, but I'll spend last 15 minutes or so and tell you about some recent work that we have done in this topic. And I should say that it's a real honor for me to have my name on the same page as the names of Raman and Pancharatnam. And as was already mentioned by Tarun, Pancharatnam was the first person who came up with the concept of geometrical phases. And in fact, such geometric phases play a fundamental role in determining the properties of these particles that I'm going to talk about. Okay, so there is, this field does owe to Pancharatnam a lot. All right, so we begin with the fractional Hall mystery. So it begins with the discovery of the Hall effect around 150 years ago. I guess you are all familiar with the effect, but let me just remind you that he discovered that so it was known earlier that if you push a current through a system in some direction, there is a potential drop in the same direction. That's called V, and we know Ohm's law. Okay, resistance is given by V over I. What he discovered was that if there is also a magnetic field present, then there is an additional potential drop in a direction which is perpendicular to the current. That's called the Hall voltage. And by using classical electrodynamics, one can show that the Hall resistance, which is defined as the ratio of the Hall voltage and the current, is given by this formula. So it's proportional to the magnetic field. It's inversely proportional to the density of the charge carriers. And so if you plot the Hall resistance as a function of magnetic field, you see a ramp, a straight line like this. And this was tested in hundreds or thousands of labs for maybe 100 years. In fact, this is a standard way to measure the density of charge carriers. So you can imagine the kind of surprise that people felt when about 100 years later the Hall effect was measured in two-dimensional system. This was done by Klaus von Klitzing, and the expectation was this red line, but he saw that the Hall resistance has this form. So it's not like a ramp, it's like a staircase. And Moreover, and this was the reason why Klaus von Klitzing was awarded the Nobel Prize, he showed that the value of the Hall resistance on these steps is universal. So it does not depend on which material you have used, what is the disorder, what's the size of the sample, shape. Not, it's given by h over an integer times e squared, where h and e are fundamental constants. So you can take two different samples and ask how accurately, how equal the value of the Hall resistance is on these plateaus, and it's equal to as many significant figures as you can measure, at least to 12 significant figures. Okay, so it's believed that this formula is exact. Moreover, the longitudinal resistance or the standard resistance goes to 0 in the region where the Hall resistance is constant. So it's not exactly 0, it's exponentially small. So it goes to 0 in the limit of temperature going to 0. So this phenomenon is known as the integer quantum Hall effect, and Klaus won the Nobel Prize for this in 1985. Okay, so this is, so the question is what's happening, what's the origin of these plateaus? Well, to understand that, we have to look at the problem quantum mechanically. So the problem of a single electron in a magnetic field was solved by Landau almost as soon as quantum mechanics was discovered, and he found that the kinetic energy of the electron is quantized. So in some sense, you can imagine, we know that classically an electron would go around in a circle in the presence of a magnetic field, but quantum mechanically, you can imagine that the orbits are quantized. Only some orbits are allowed, and therefore only some kinetic energies are allowed. These are called Landau levels. Moreover, Landau found that the number of spaces in each Landau level is given by this formula. Okay, so the number of spaces is equal to how many electrons you can put in a Landau level. Okay, so this is the maximum number of electrons you can put in any given Landau level. One thing, so this is an important number. I will talk about this again and again. This is called the filling factor. It's just equal to how many Landau levels are filled. So for example, if you look here, you count 2 and 1/3 of Landau levels are filled. This is just total number of electrons divided by number of spaces in any given Landau level. Okay, so in general, we don't know what the ground state is, because we could have put this electron, here or here. So there are lots of possibilities, except when the filling factor is an integer. So, okay, let me go a bit carefully. So let's switch off the interaction between electrons for a moment. Okay. Then, when the filling factor is an integer, we know precisely what the state is. So at filling factor 1, I fill 1 Landau level exactly, and this is a unique state. I know the wave function for the state. I will denote it as phi1. At filling factor 2, this is the state, right? 2 filled Landau levels are filled compactly, and this is a unique state. I know the wave function, and so on. Furthermore, there is a gap to excitation. So I have to kick this electron into a higher Landau level, which causes a gap. The gap actually gives stability to the state. So let's say you switch back the interaction on, the gap does not go away immediately. If the interaction is too strong, at some point it will go away, but it survives for many situations. And this fact that there is a unique state with a gap to excitations is what is responsible for the integer quantum Hall effect. Okay, so the integer quantum Hall effect is well understood because it's a phenomenon we can understand in terms of non-interacting electrons. So just to summarize, what's the origin of these plateaus? Well, this is the origin. So we know precisely the states, unique states with a gap. So, so a very nice effect has been discovered. It has been explained. So you all feel happy. But it turns out, and this is one of the twists, it turns out that, oh, by the way, there is also a topological interpretation, so that involves Berry phases and so on, but that was discovered by Haldane and Thouless, and for which they received the Nobel Prize in 2016. So just a couple of years later, these gentlemen went to yet higher magnetic fields, and they saw a step where Hall resistance is h over a fraction times E squared, and the fraction was 1/3. So what's happening here? So this was in 1982. In 1983, Bob Laughlin, he wrote a wave function. It's an ansatz wave function for the ground state at filling factor 1/3. And we'll come to this wave function again later on, but for this work, 3 of these 4 gentlemen got the Nobel Prize in 1998. So this one discovery of 1/3, theory of 1/3, again you feel good. You know, so this is a point where if the experimentalists had stopped, we would all be happy. Fortunately, they did not. And they you know, cleaned up the sample, they went to lower temperatures, and very soon the figure started to look like this. So there are lots of plateaus now, lots of steps. 1/3, this is 2/5, 3/7, etc. And for all of these, again, the longitudinal resistance vanishes. So you can either look here or here, and very soon, you know, the figure, the trace of resistance as a function of magnetic field started to look like this. So I almost always make the claim that this is the most beautiful single trace taken in physics. So this is just measuring the resistance as a function of the magnetic field, and you see a huge amount of structure. It's not noise. Okay, everything here means something, and we'll see that there is beautiful underlying physics which explains all of this. So the fractal quantum Hall effect, we'll see, is the most stunning manifestation, or it's one of the most stunning manifestations of quantum mechanics at the macroscopic scale, and it's also one of the most striking mysteries that nature has presented us with. So remember my first slide where I talked about lots of facts? Well, here there are lots of facts. So there are lots of these minima. So if you count how many minima are seen, that's like 100. So we have seen that many different fractions. For each fractal Hall state, you can measure lots of properties. You know, you can measure collective modes, gaps. You can measure various transport coefficients, thermal Hall effect, etc. You can measure them in different types of samples. You know, you can take graphene, quantum wells, etc., and you can tabulate all these numbers. So there is a huge amount of data. And to this, we theorists can add our own data. So we can take some number of electrons, put them on the computer, solve the problem exactly, solve the Schrödinger's equation exactly. We get all of the eigenstates, eigenenergies, and there's a huge amount of information here. Okay, so now let's look at what is the problem that we would like to solve. So I will first write down the minimal model. So the general model would be you take a Hamiltonian which has the kinetic energy, interaction energy, Zeeman energy disorder, and you want to solve the Schrödinger's equation. Let's simplify our lives a little bit by pushing the magnetic field to infinity. in that limit, this term and this term, they both are proportional to B. They are much larger than this interaction term, which is proportional to square root of B. So I'm going to minimize this by putting all electrons in the lowest kinetic energy state, lowest Landau level. I will minimize this by assuming that all electrons have spins pointing in the favorable direction, and I'll just switch off disorder, and I end up with this minimal Hamiltonian where I have chosen my units so as to get rid of E squared and so on. Okay. So you notice that there is no parameter here. In particular, there is no mass, no kinetic energy. You know, electron mass is not a parameter for the fractional Hall problem. So we would like to solve this problem for the lowest Landau level. Okay. So the mission for the intrepid scientist, theoretical physicist, is to identify the fundamental principle underlying the fractional quantum Hall effects and to develop a microscopic theory that explains, unifies, predicts, and also enables parameter-free calculations. Okay, so let me tell you why this cannot be done just from pure theory. So the expectation is that we expect at certain fractional values of the filling factor unique gapped ground states. So that's what we would like to get. That's what experiments are telling us. Here, if we switch off the interaction, let's say filling factor is less than 1. If we switch off the interaction, we don't have a unique ground state. You know, there are more spaces than there are number of electrons. So we can arrange the electrons in the available spaces in lots of different ways. They're all equivalent as far as our theory is concerned. This is in fact the most strongly correlated system in the world. So the strength of the correlations is often measured by the ratio of the interaction energy to kinetic energy. Here there is no kinetic energy. The only energy is the interaction energy. I can also tell you that there is no exact solution to this problem. This may bother some of you, but it doesn't bother condensed matter theorists, you know, because even the problem of 3 interacting particles is not exactly solvable. So if we insisted on exact solutions, we might as well do something else, okay, because there are no exact solutions. But we make progress by doing perturbation theory, okay. The problem here is that even perturbation theory is not available because there is no small parameter. You know, you have to have some small parameter. So you start with an H naught and you perturb around that. Here we don't know. There's no parameter in the problem. Now just to get a feel for what we are dealing with, let's take a system, let's say filling factor 2/5, 100 electrons, and ask in how many different ways can I put electrons in the available spaces. The number is 10 to the power 69. So this is like a baby system. A typical experimental system has 1 billion electrons and you end up with such ridiculously large numbers. So just to give you a feel for how large these numbers are, if you count the total number of quarks in the universe, that's around 10 to the power 80. So, so the question is, one of these, so there are all these distinct configurations, and one entangled combination of those is the ground state that we are looking for. But the problem is not as easy as trying to find a needle in a haystack. It's more like trying to find a quark in the entire universe. Not even knowing where to begin, how are we ever going to find out what's happening? Okay, so so when we learn physics, you know, when we take physics courses, we get these problem sets. This is the problem, find the solution. We find the solution. Well, that's not how research works. in research, when you're doing research, you have to keep modifying the problem as well. You have to keep modifying the question, okay, as you learn more. So if the question is sufficiently well developed, refined, and sharpened, it almost has the answer in it. And at least it shows to you the way to the answer. So let's ask the question, okay? We can ask, what's the physical origin of the fractional Hall effect? Or what's the organizing principle? What is the mechanism of the fractional Hall effect? You know, these questions are not particularly helpful. They are all asking the same thing in different ways. They are saying, what's happening? You know, a question that is a bit more useful is this: what are the weakly interacting emergent particles in the fractional Hall effect? So now you might at first say, how do we know there are any weakly interacting emergent particles? Well, it's actually, I would say it's a fundamental law of nature that strongly interacting particles combine to form some weakly interacting particles. It happens all the time. So you start with quarks, you know, they combine into protons, neutrons, or if you let's say, I mean, I like that analogy. If you take electrons, quarks, put them in a bucket, shake the bucket open, you might find helium-4 atoms. Why? Because those are more weakly interacting. So it's almost like a law of nature. It's kind of a rule. It's not an exception. Now, this question is almost the final form, but there's one more step. Let's ask, suppose we had some weakly interacting emergent particles, what would they do? Well, the only thing they can do is show integer quantum Hall effect. So the question that is most useful is, can we understand the fractional quantum Hall effect as the integer quantum Hall effect of certain particles? Now, another way to motivate the question would be the following. So I have shown this plot to you earlier. You see, there is a remarkable thing about this. It has both the integer Hall effect and the fractional Hall effect. Okay, and to make the point that I would like to make, let me erase all the numbers, and then you notice that you cannot tell fractions from integers. They all look identical. So you would, I mean, it would seem natural that there is some deep connection between these, and the question is, can we unify these? So this is something that I had noticed, and I was, you know, I mean, I didn't know what to do with this. But in 1988, when I was a postdoc, suddenly I had an idea which kind of changed my life. Okay, before that I was just doing this or that. But after that, and before this instant, when I had this idea, I was not working in fractional Hall effect. After this, I was. So it kind of set my career. Let me just say that, of course, nothing happens in vacuum. There were lots of beautiful theoretical ideas and many experimental facts that played a role in my thinking, which I mentioned here. I owe an incredible deal of gratitude to these works and these people here. So what's the idea? Okay, that's my only fancy slide here. Okay. So the idea was that if we assume formation of particles which are called composite fermions, then a lot of these experimental facts suddenly make sense. The definition of a composite fermion is that it's an electron which has an even number of quantized vortices bound to it. Pictorially or intuitively, we often think of it as the bound state of an electron and an even number of flux quanta, where a flux quantum is defined like this. This is a composite fermion carrying 2 flux quanta, this is carrying 4, and this is carrying 6. Why can we replace quantized vortices by magnetic flux quanta? Because both are topologically similar in the sense that a closed loop around a vortex gives you a phase of 2 pi, and the same is true for a closed loop around a flux quantum. These are topological objects because the phase does not depend upon the size or shape of the particle, or loop. You just have to go around it. No matter what path you take, you get a phase of 2 pi. Okay, so this one slide gives you the intuitive picture of composite fermion theory. The postulate is that strongly interacting electrons transform into weakly interacting composite fermions by binding 2 or 4 or 6 flux quanta, which can point in either direction. The fundamental property now of the system is that composite fermions do not see the magnetic field that they have bound to themselves. They see the remainder magnetic field, which I call BCF. It's equal to the external field minus even number of flux quanta removed per particle. Okay? So composite fermions, like any non-interacting fermions, now form their own lambda-like levels. These are called lambda levels. They have a filling factor which I denote by nu CF. And the electron and the composite fermion fillings are related by either this or this equation. They're the same equation. So the whole picture is now that this strongly interacting system has been mapped into a weakly interacting system of fermions. Okay? We can go one more step and write ansatz wave functions. So these are wave functions of non-interacting electrons at some filling factor nu CF, and here I can get the ground state, excited states, and so on. I know all of them. I multiply by this factor which attaches 2m quantized vortices to every electron to turn it into a composite fermion. So this is basically the wave function I want, except that I would like, remember I restricted my space to the lowest lambda level. This wave function is not strictly in the lowest lambda level, so we are just going to project it into the lowest lambda level by hand, and we are going to say that this gives us wave functions for strongly interacting electrons at filling factor nu in the same order. Okay? Notice that we have now, using this ansatz, we have written wave functions for all eigenstates at all filling factors. And one of the amazing things is that if nu CF is an integer, remember this is a unique wave function, and therefore I get a unique wave function, which is remarkable given that there was a huge amount of ambiguity for the electron problem. So if you look at the problem in terms of electrons, it's a mess. You look at it in terms of composite fermions, you get unique solution. The composite fermion carries geometrical phases. So okay, since I want to make a connection with the work of Pancharatnam, a microscopic way of understanding the magnetic field BCF is you drag a composite fermion in a closed loop and ask what's the phase associated with that loop. It has two contributions because an electron has gone around a loop. That gives you an Arna-Bohm phase. Also, two vortices have gone around a loop, and each vortex is a phase 2 pi for every electron that's enclosed. So you get total phase given by this, which you equate to the Arna-Bohm phase coming from some effective magnetic field that gives you the magnetic field seen by composite fermions. So this geometrical phase is fundamentally responsible for the BCF. So I just want to mention that there is another approach, which is a field theoretical approach to treat composite fermions, but I'm not going to do anything with this in this talk. Okay, so I have told you what composite fermions are, but I have not given you any reason to believe in them. And it's natural to ask, do they exist? And if so, in what sense do they behave as particles? Horst Stormer, a discoverer of fractional Hall effect, wrote a paper with the title, How Real Are Composite Fermions? So how do we know? Well, the theory has to explain experiments, so no matter how much I might be in love with my theory, at the end of the day, experiments have the final say on it. And so the question is, what does the theory explain? So I will show you that this theory successfully predicts or explains thousands of facts in a supremely unified fashion. And let's go over them quickly one by one. So these will be categories, I won't have thousands of slides here. Okay. So first of all, origin of the fractional Hall effect. So let's consider these filling factors, electron filling factors. We feed this nu into the formula for the composite fermion filling factor, and you find that it's an integer. So you notice that here we have a unique gapped ground state. At 1/3, filling factor 1/3 is seen like this, 2/5 is seen like this, 3/7 is seen like this. So this is the solution for non-interacting composite fermions. Now you may say maybe there is some weak residual interaction, but since there is a gap here, it gives stability to the state. And this actually tells you why at all, in the first place, why is there a gap at fractional fillings? So this explains that. It also explains the prominently observed fractions. So if you look here, there are fractions 1/3, 2/5, 3/7, and so on. They follow this sequence, which is integer Hall effect of composite fermions carrying 2 flux quanta. These follow integer quantum Hall effect of composite fermions carrying 4 flux quanta. These are the fractions that appear. In fact, let's compare. So what we see here is very similar to what happens here and what happens here. So let me take this figure and put it here. So I have just moved that leftward. This and this are exactly the same, but you notice that the fractions here, they line up with the integers. So it just looks like the integer Hall effect of some particles. There is evidence for composite fermions carrying 6 flux quanta, 8 flux quanta. So at least 4 of these species have been seen. Lots of members are seen along a sequence. In fact, in the best samples, best quality samples, they have seen 14 or 16 members along these sequences. Okay. So this is, what I showed you earlier was gallium arsenide quantum wells. These are experiments on monolayer, bilayer graphene, and again, all of these fractions are precisely what the composite fermion theory predicts. So it correctly predicts the prominently observed fractions. In fact, all of these fractions have odd denominators. So earlier there was this question, why do they have odd denominators? That is explained. All fractions are predicted in one go. So remember, Laughlin had 1/3. So from his theory, you don't know why there is 2/5. but here we get all of those fractions in one step. So it unifies, the theory unifies all fractions, but it also unifies the fractional and the integer Hall states. And notice I have not used any microscopic theory so far. Another success was a new phase of composite fermions, which is a metal. So let's, I mean, this is always a good idea. You take any theory, push it to the limit, do a stress test. So, and see what you get in that limit. Like Einstein's theory of general relativity gives you black holes in one limit. Here, let's take the limit of p going to infinity, which corresponds to electron filling factors given by 1/2. So it's half-filled lambda level. Here, it turns out when electrons convert into composite fermions, they eat up all of the magnetic field. So we end up with composite fermions in 0 magnetic field, and therefore you say, okay, they form a metal. This was predicted by Halperin, Lee, and Reed. And there have been hundreds of experiments which have tested this. Okay, so we know how to test metals. There are like Shubnikov-de Haas oscillations. So there are lots of different tests, and they have all been performed here. So this shows that composite fermions are actually more general than fractional Hall effect. So fractional quantum Hall effect is only one of the phenomena they show. They also show a metallic phase. So we have unification not only of fractional Hall states, but also non-fractional Hall states here. And even to understand all of these experiments, so far we don't need any microscopic theory. Okay, let's now do a microscopic validation. And this, to me, in my thinking, this was the most amazing of all. So I have shown you these wave functions. Now what I'm going to do is do 2 different calculations with no approximations. Both are exact with no parameters, and put them on the same plot. Okay, so one calculation is I'm going to obtain the exact spectrum by a brute force diagonalization of the Coulomb interaction on the computer. The second is I'm going to obtain the spectrum using composite fermion theory, and I'm then going to compare these 2 results. Okay, so a brute force diagonalization looks like this. So this is similar to what we have in atomic physics. You have some atom, you can plot its spectra. So that's what we are doing here. It's a system of 18 particles. So it turns out that a nice geometry is to wrap the 2-dimensional sheet onto the surface of a sphere and subject it to a radial magnetic field, which can be done by placing a magnetic monopole at the center. But this is just a choice of boundary conditions. The quantum number for this geometry, the natural quantum number is the orbital angular momentum. So you notice that there is a state here, this is a ground state, you have a bunch of states here. This system is not very small. So here I plot the total number of basis states or total number of independent electron configurations at, let's say, this angular momentum. You have 2.3 million. So, for example, this state, to define this state, you need 2.3 million coefficients. Okay, it's a linear superposition of 2.3 million basis functions. So it's a fairly large system. So what does composite fermion theory say? Well, this is at filling factor 3.7, so it will say this is filling factor 3 of composite fermions. These are probably some excited states like this, and we know precisely the wave functions for this. So I'm going to take this wave function, calculate the Coulomb expectation value, and we get these dots. So to me, when this first happened, so when I had first written the wave functions, I thought, okay, they will give some 0th order approximation to the actual state. And when we actually looked at this, it was shocking to us that they basically give you the exact state, almost, okay? This is what I say, what I mean by cracking the code. So suppose you just did the computer calculation, and the computer would spit out a bunch of numbers. These are coefficients along these different directions, or projections along these different directions in the Hilbert space, and you have no idea what the numbers mean, okay? What composite fermion theory says, well, I can use this simple picture and give you a state which is almost the same, but this tells you what the physics is, for not only for this, but it gives you physics for all of the states, okay? In fact, in the beginning we said, wow, this is so good, but then at some point you say, well, there is some little bit of deviation here, so what do you do? And then you say, well, how about the higher energy states? So we can do composite fermion theory. So we can now add these higher energy states. So these are states where we are exciting by 2 quantum numbers, and do diagonalization within this small Hilbert space, and now see the level of agreement. It's almost exact. So, and we can understand all these states successively, and basically get exact results whenever we need it. You can get results to whatever accuracy you need them. These are quasi-particles. So here there are 2 plots. This is density of a quasi-hole. So quasi-hole is a missing composite fermion. A quasi-particle is an extra composite fermion. These are densities from this wave function and the exact densities. You probably cannot see that there are 2 curves. They fall on top of each other. Now, I took the example of 3/7, but this is true at all filling factors. So this is 1/3, this is 2/5, this is in between. So you give me any filling factor, and I'll tell you what the exact spectrum is. So miraculously, the infinite choices of the electron problem disappear when we view it in terms of the composite fermions. And a single equation gives all low energy eigenstates at all filling factors. In fact, people ask me, so you may know Senthil at MIT, he was asking me, why is this so good? I don't know. Somehow it works beautifully, but no matter what, at least this is an absolute microscopic confirmation that there are composite fermions. So Horst-Stormer, after this, he said, well, they're as real as Cooper pairs. Am I taking too much time? Maybe I'll take 5 minutes or so. Okay. So what have we learned so far? Well, we have learned, this is the picture for integer quantum Hall effect. This is the picture for fractional Hall effect. And that at half-filled lambda level, so the filling factor is half here, we have a Fermi sea of composite fermions. So in the title of my talk was where strange particles rule. Well, there are other strange particles. One is called anions. How many of you have heard of anions? Okay, not all. So let me just say that if you have two indistinguishable particles, you exchange them, you get a phase, you get a sign of plus or minus 1, plus 1 when these are bosons, minus 1 when they are fermions, right? This is quantum mechanics, Pauli principle. It turns out in 2 dimensions, there are other possibilities. So if you take these two particles, different colors are just to show them separately, but think of them as the same, the identical particles. You exchange them, you find that in addition to plus or minus sign, you can actually get some phase factor. And for the quasi-particles of the fractional Hall state, the phase factor is this. Now, if these were bosons or fermions, you would get 0 or pi, okay? So these particles are generalizations of bosons and fermions. They have any statistics, so they were called anyons, a name given to them by Frank Wilczek, a nice name. So this was a concept that actually had been proposed by two Norwegian theorists just from pure thought, and within a few years they found a realization in fractional Hall effect. So so theorists have believed that there are anyons in fractional Hall effect. Experimentally, it's evidence for these have been seen only within the last few years. Okay, so once you start looking at the problem in terms of composite fermions, you can ask many more questions. You can say, what's the mass of composite fermions? You can ask, well, how about the magnetic moment? Do they show some other states? So it turns out that one can ask lots of these questions and answer them. So they have integer Hall effect and metal, but I'll say a few words. They can also form a superconductor. They have bilayer states. They can have their own fractional Hall effect. They can have stripes, crystals. So pretty much all of the phases you can see for electrons, they occur for composite fermions as well. And one can study lots of different properties of them. Okay. So if you are interested in this, you can look at some chapter, whatever chapter contains the topic of your interest. But I'll just mention a few of these states very quickly and call it a day. So we had assumed that all electrons have the same spin. Right? We assume that B is infinity, so the Zeeman energy also goes to infinity. But it turns out that experimentally one can reduce the Zeeman energy. And the composite fermion theory then predicts what are the possible spin polarizations of the fractional Hall state. So just to give you an example, let's take filling factor 4 dynes. That maps into filling factor 4 of composite fermions. So here they can all have the same spin, or 3 lambda levels have the same spin, 1 opposite spin, or 2 and 2. So there is a spin singlet state, partially polarized state, fully polarized state. So for all fractions, we can list what are the possible polarizations, and those are precisely what experiments see. We can go further. So these stars are the Zeeman energies where they see transition from between this and this state, and by taking into account everything, like finite width, lambda level mixing, and so on, we calculate these circles. And you can see, we can actually explain things quantitatively. The critical Zeeman energies, they depend on very small Coulomb energy difference between the competing states, and we can calculate that small difference within a few percent. We predicted that if you increase lambda level mixing, so if you bring lambda levels close to each other, then at some point there would be a Wigner solid phase. So this solid line is the theoretically predicted phase diagram. Experiments found extremely good agreement. So here for liquid they find, so at 1/3 they go up and they find it remains a liquid. Here, this is a liquid, and so open symbol is a liquid, the solid symbol is a solid, and they find that there is a transition from a liquid to a solid here. So very good agreement. I mentioned superconductor. Well, there is a little bit of story behind that. So I earlier told you that there is no fractional Hall effect at even denominator fractions, but it turns out that many even denominator fractions have been observed. So how do you understand those? The picture is that first there is a metallic phase, but the metallic phase is unstable to pairing of composite fermions, which opens a gap and therefore shows you fractional Hall effect at those filling factors. So in fact, this is another mechanism for fractional Hall effect. So one mechanism was integer Hall effect of composite fermions. This is a superconductor of composite fermions. So we have done detailed microscopic calculations to study this instability. So just to give you one example, so I'm going to skip this. Let's say we change, so this is the density, this is quantum well width. We find that in this region, we predict it's a metallic phase, and in this region, it's a superconducting phase, and this is the experiment. So you can see extremely good quantitative agreement. We predicted that as you increase lambda level mixing at filling factor 1/4, you would see a transition from a metal to a paired state, and indeed they see that experimentally, so this was confirmed. We have calculated the angular momentum of the pair, so it's either P wave, F wave, for many of these, so it's still to be tested experimentally, but at least the theoretical prediction exists. And these superconductors have given rise to another strange particle, which are called Majoranas. So, I mean, there's the story about Majorana. He came up with a real solution to Einstein equations, and those are particles which are their own antiparticles. They were called Majorana. As far as we know, there is no Majorana particle in nature, although there is still some question as to whether neutrinos could be Majorana particles. In fractional Hall states, we say creation operator is equal to annihilation operator. That's called a Majorana particle. And it turns out that these superconducting states have abricose vortices. They harbor Majorana particles. Okay, so each abricose vortex has a Majorana tied to it. It's approximately half of a composite fermion. So we have split, when you make Majorana, it has split a composite fermion. So if you bring two vortices together, I have half a composite fermion here, half here. It can give either one composite fermion or zero. Why zero? Because it can be its own antiparticle. So you have two possibilities. It's not been confirmed, but it's been proposed that it could be a qubit. So this 0 or 1, this could be a qubit. It's been proposed that this would be a topological qubit. So it's fault tolerant. So if you could make this, you won't have to do any error correction. That's the claim. And recently, there was this news by Microsoft about Majorana 1. So this is not using fractional Hall effect. These are Majoranas produced in some other, in semiconductor nanowires. But this is, the line of this, the chain of events that led to this had fractional Hall effect somewhere on the way. I mean, this claim is controversial. It's not everyone believes in it, but we'll see what happens with it in the future. And the last thing I would like to say is that there is another twist, composite fermions without a magnetic field. I won't tell you how this happens, but in certain twisted bilayer systems, Uh, these fractional quantum Hall effect has been seen without the application of a magnetic field. This goes under the name fractional quantum anomalous Hall effect. The fractions they see are precisely the fractions predicted by the composite fermion theory, and there is also evidence for a Fermi or a metallic state of composite fermions in these systems. So when this happened, Horst Stormer, he kind of retired about 15 years ago, and he is completely disconnected with the physics world. But when this happened, I could not resist. I sent him an email saying, Horst, did you know that fractional Hall effect has been seen without a magnetic field? He said, absolutely mind-boggling, weirder than we ever thought. And I think this kind of goes for the entire field. Let me say, there are still open problems, but a couple of dreams that I have. One would be that composite fermions could be harnessed to do something useful, technology, maybe through Majorana's or who knows what. But another dream would be, it's kind of, it happens all the time, structures that we find in one field show up in some other field, like the spontaneous symmetry breaking of the Higgs mechanism of superconductors played a role in unraveling the standard model problem. It's kind of appealing that certain structures revealed in the study of composite fermions and the fractional Hall effect could provide a clue into some other important problems in physics. That would be fantastic. And let me say, all these calculations I showed, I could never do them. I have had the great fortune to have some fantastic graduate students to whom I owe everything. So with that, of course, I thank them, but let me also thank you for your attention.
Yeah, okay. Is there a question over there?
Thank you, sir, for the nice talk. My question is that, when we are making this composite particle, are the electron keep their individuality in the composite particle? And if yes, whether Pauli exclusion principle is respected or not?
Okay, so the first part of the question is, do the electrons keep their individuality?
Yeah.
So, from our perspective, the composite fermion, I called it a very strange particle. But suppose you were a little human being or somebody with intelligence living in this two-dimensional world, you would think of composite fermions as the fundamental particles, and electrons would be very strange particles for you, because the excitations don't have electrons. You create these excitations, and they are anyons. So in some sense, there are no electrons in the fractional Hall problem. Okay. Now, Pauli principle. Of course, the electrons, all the wave functions I have shown you, they are completely antisymmetric, and composite fermions are also fermions. So, the wave function is antisymmetric. So yes, Pauli principle is obeyed completely. It's not violated in this system.
Okay, thank you.
Can there be any analog of composite fermion in 1D or third dimension, like 3D?
So in 1D, that's of course a very interesting question. The thing is that this vortex is defined in two dimensions.
Majorana can be in 1D, right?
Majorana can be in 1D, yeah. So, okay, so let me answer your question. So composite fermion is the bound state of an electron and a vortex. Vortex can be defined in 2 dimensions because as you go around a vortex in a loop, you get a phase of 2 pi. This property is lost in 3 dimensions because you can lift this loop off the plane, and so the concept of loop enclosing a point does not exist in 3 dimensions. You could imagine maybe there are some other topological excitations which are stable in 3 dimensions, and they could bind with electrons. Some hedgehog or something like that could bind with the particles to form new particles. That could happen, but not these ones. In 1D, so the Majorana particles can, okay, so Majorana particles, they occur more generally in superconductors which are called topological superconductors, whose order parameter has the form px plus ipy. So you could have, in 2 dimensions you would have vortices. In 1 dimension it becomes, so there is a vortex trapped at the end of the wires, at the 2 ends of the wire. And we can create something analogous to that even for fractional Hall effect. So if you take a fractional Hall system and make it sufficiently narrow wire of that, then it turns out that the inter-edge scattering will open a gap and you will end up with 2 Majoranas at the ends. Okay, so
you're saying there is an analog for 1D at least.
there is an analog for 1D. That's correct.
Thank you.
Other questions?
Okay, you showed some of these wave functions of this composite fermions, and you said that earlier also Laughlin wrote down some wave function. So, I'm know nothing about this field. So this in this wave function, what does this Z stand for? Are these wave functions are functions of space, as in or elementary quantum mechanics, or how do you are this? You put them as ansatz, which explain some experimental facts, or you can get them out of Schrödinger equation in some situation, or would you elaborate some in this?
Yeah, just 1 second. Let me go to, okay. So I should have emphasized Z or Z stands for x minus Iy or x plus Iy. Okay, so it's a coordinate of a particle represented as a complex number. So these are solutions. So there's nothing relativistic. You just take Schrödinger equation that I showed you and you solve it. I mean so the claim is that on the one hand I could do exact diagonalization, work very hard to get the solution, and I have no idea what that means. I mean, even with exact diagonalization, I will discover that there are gaps at certain filling factors, but I don't know what the physics is. With composite fermion theory coming at the problem from a completely different direction, I would say, well, this provides an extremely good representation of the exact solutions, but it also tells me the physics. If I look into this, I can see that I have a wave function of non-interacting particles where times this factor which binds vortices, so I can see, okay, there are composite fermions here. Okay. So let me also say we don't know how to derive this. So these are ansatz wave functions. So one can write field theory, but we have no idea what Feynman diagrams would have to be added to get these wave functions.
So you mentioned that from this Landau theory, one can get fractional quantum Hall effect, and then to go beyond that to get this composite function fermions, do you have to do something extra into Fermi theory?
Landau theory just gives you single particle wave functions.
Okay, these are.
With Landau, so it gives you the basis, okay? It tells you what the Slater determinant basis would be. If you solve the interacting Hamiltonian, if you just put it on the computer, that will give you fractional Hall effect. But we don't know what it is. On the other hand, here this proposes a way which, gives the physics which can be tested in any which way, okay? I don't know if I have answered this question.
Yeah, I get some idea.
Some idea, okay.
Other questions?
Yeah, you said each of these composite fermions entrap even number of fluxes. So is there a deeper reason for that, or why not odd number of fluxes?
Excellent, excellent. Okay, I mentioned anions. So those who know about anions, they will know that if you take an electron, you bind fractional number of flux quanta, it becomes an anion. If you take an electron, bind even number of flux quanta, it becomes a fermion. If you bind an odd number of flux quanta, it becomes a boson. Now you could say, well, why not bind odd number of flux quanta? The problem is that bosons do not repel each other. Okay, so bosons like to clump together. Fermions, they already have Pauli repulsion built into them. So for a Hamiltonian which is trying to keep particles away because it's a repulsive Coulomb interaction, you would think that it's better if they become fermions rather than bosons. Okay, that's an intuitive answer to your question, but at the end of the day, the proof is in the pudding. So we show that if we do make fermions, we can give a complete we can give a complete description of the state. Okay.
Thank you.
Other questions? Let me
We are
ask
all
just
hungry.
two quick questions. So one is that, so this fact that the composite fermions are weakly interacting, do we understand that by saying that these vortices keep them maximally apart from each
Yeah.
other? And how do
That's-
you estimate the residual interaction? Is there a systematic way?
Okay, so good. So if I ignore this, so I'm just elaborating on the first part of your question. If I ignore this factor, if I bring two particles close to each other, this vanishes as a single power because this is a wave function of fermions, but this also vanishes as power 2m. So the wave function vanishes very rapidly when I bring two electrons close to each other. So those configurations they have lower probability. This is why it seems like a good wave function. Of course, when you project it into the lowest lambda level, this property goes away. So there is only 1, 0. So somehow you have to think, okay, maybe it still keeps good correlations, okay? But for that, you have to actually do the calculation and see. But the second part of your question is, how do we know what the residual interaction is? So the residual interaction between composite fermions is inherited from the interaction between electrons, okay? To calculate the residual interaction, one can do it, but it requires hard work. So I cannot write a formula which just tells you what the interaction is. So what you can do is you can write a wave function where there is a composite fermion, a quasi-particle here. You calculate the energy as a function of the distance between them, and you'll find the interaction. In fact, let me also okay, so I showed, so the beauty is that the interaction between composite fermions is weak, and sometimes it can be weakly attractive. There's nothing that stops it from being weakly attractive. So I had shown a figure where We calculated whether the system becomes superconducting or not. So the figure was as a function of density and quantum well width. So as you change the density and quantum well width, the interaction between electrons is changing. The effective interaction between composite fermions, at some point it becomes attractive, and that's why we get pairing of composite fermions. Okay.
Tarun has a question.
Yeah, knife questioning. Is there an analog possible in non-abelian case 3? I mean, you have a magnetic field which is our standard electromagnetic theory, right? So
Yeah.
in non-abelian case theories, are there magnetic field analogs which can allow you such structures happening with the particles they pair with? And if so, if does it allow a phenomena in 3 dimensions or
Yeah,
3 plus
I
1
think
dimension?
that's a very good question, but I am not qualified to answer it. Smita, do you know? No.
I think it's a really good question.
It's
I
a
don't
good
think
question. I think that's
at present there is, but it's probably possible to construct something.
okay.
So
I think that's
open question.
that's a very good question. Yeah. So,
Hi. So you have said that one can build fault-tolerant QC platforms from Majorana particles. So is that a fundamental characteristics of Majorana particle? I mean, what is the connection?
connection. I mean,
Is that a property of Majorana particle?
No, no. I mean, the idea is okay. So the reason it's fault tolerant is you store information non-locally. So let's say I have 2 Majorana particles here, which I can put either in 0 or 1 state. Now I can move these Majoranas far away from each other.
Okay.
They would still stay in the 0 or 1 state. But the point is that any local perturbation is not going to destroy that 0 or 1. So therefore, it should be fault tolerant.
I see.
Okay, that's the idea. Okay, this is an idea. It's not been demonstrated, and in fact, I mean, so many companies, you know, like Google and IBM and so on, they are following different strategies toward quantum computation. Microsoft is following Majorana strategy, so they are trying. It's not been demonstrated yet, but let's see what happens. Okay. So even I mean, in fact, the field has been kind of very full. So there have been claims of Majorana's observation, but later those were found kind of fraudulent. So the field has been, yeah, it's, anyway, we'll see what happens.
Any other questions? Okay, so if not, let's thank Professor Jain again for the wonderful talk. And I would now, token of thanks, I would invite our director, Professor Tarun Saradip, to hand over a token of appreciation.
Oh.
Thank you for the wonderful talk. So this is something for you to remember the
Oh.
experience in Nara, right?
Thank you.
This is his face. And also
Can you take a picture of all of us also? So yeah.
and also the collected works of Pancharatnam.
Oh, okay. Thank you.
So much. Wonderful.
Well, can I sit here and?
Thanks, sir.
Will you send me a copy? Yes, sir.
These works in the purchase, but double as a photographer also, when required. Multiple people taking up various roles.
आप कैसे देखेंगे?
Vijit will